Ladies and gentlemen, let's look at the two points. The first rod and the second rod, where the second rod is connected to the earth. Meanwhile, is earth. If, look at here, if the voltage is positive 1, what is the meaning of 1 volt? 1 volt means that the energy needed for one coulomb of charge to move from one point to another point. That means that if from here to here, means while this side is connected to earth, that means that it will be 0. So we look at here distance x. Once the x from here is maximum is 1, let's say it's 1 watt, that means that when the distance increase, so the voltage or the potential energy will reduce. Potential difference reduce. What happens if you observe the gradient? So the gradient increase where is negative gradient. So meanwhile, from here to here, what happened again? From 1 watt to 2 watt, the number of line increase, double. So this means that the stronger, the more the voltage, the more the potential difference. So the stronger the electric field. So from here, dV over dx is the electric field strength. Electric field strength is equal to negative dV over dx. And what happened if negative 1 watt? Negative 1 watt means that the energy required, still the same thing, the energy required to move the electron from one point to another point, but it's in opposite direction. So negative 1 and negative 2. Still, we can get the electric field strength equal to negative dV over dx. And what is the relationship? The electric field strength E is equal to negative dV over dx, where the negative gradient of the Vx graph. This one is the negative, although it's positive, right? Positive become negative. So the electric field is in opposite direction. If negative, negative like that. But what happened if I convert it, I change to positive 2? That means that if like that, this is the negative gradient, right? Negative, this means negative dV over dx, where dV over dx is negative. Negative times negative become positive. So electric field from this side to 0, that means that it is positive. Next. Let's go to the next slide. E is the electric field strength. Kekuatan medan elektrik. So electric field strength, the graph, the electric field strength reduce when the distance increase. The area under the graph, that means that just now the charge is pulled from infinity, right? Infinity to a point of P maximum, where the kinetic energy reduced to 0, becomes 0 before it repels. So this means that the energy just now is the energy. So here to move is to the near to the point P. This means the stronger the electric field. So how about the electric potential? Electric potential V is equal to negative integration of E dx, where it's from infinity to a point of R. where actually is the integration means that integration E dx. This means that we determine the area under the graph. The area under the graph of Ex will be the electric potential. The area under the graph represent the electric potential. Summary. The relationship between the electric field strength E and the electric potential V is E equal to negative dV over dx, where V is equal to negative integration from infinity to R for E dx. Next slide. Now we'll go to the electric potential due to point charge. Let's look at a positive point charge. Positive point charge, let's say with 1 Q. Positive Q, let's say 1 coulomb, for example. Positive charge, where the direction of the electric field is up. The line show that the pattern show that represent the electric field. Each of the line means that there is the electric field line to a point P. So from here, we look at here, the electric potential V, electric potential at point P, this point, is given by E equal to E equal to Q over 4 pi epsilon R squared. So Q is the how much of charge and the R is the distance. Others pi and epsilon will be a fixed constant. As a result, the electric potential, if the electric field strength is equal to Q over 4 pi epsilon R squared, so the electric potential V at point P will be the negative integration of E dx, right? E dx, right? So at the end, we get that it will be Q over 4 pi epsilon R. So if we want to find the V electric potential, that will be Q over 4 pi epsilon R. Just now said that per charge, right? So this means V is the energy per single charge, Now, next slide show that the point charge of positive point charge, where there is the green line, red line, and blue line. What happened to the green area? This means that at the end, boundary of the green line, where each of the green line have the same distance from the positive charge. This means the same distance, same radius of the sphere, of the circle, green color circle. This means that we call that at this point, for example, first point, second point, any point on the green line will have the same potential surface. So we call that this, the green color, all of the green line or at any point on the green line have the equal potential. If there is 5 watt, here also 5 watt. Understand? So for the red line, this means that of purple color, so or maroon color, anything. This means that for the red line, they will have the same equal potential. We call that is the equal potential. Same with the line, the point at the blue on the blue line. Any point on the blue line have the same potential. So we call that this blue line are is the equal potential surface. Let's look at the point charge. A point charge with positive. Let's look at the graph of V against R. Potential, electric potential against R. So for the first equal potential, as we know that V is inversely proportional to the distance, right? So that means that the nearer the distance to the charge, the stronger the electric potential. What's mean by electric potential? Okay, that means more energy needed to bring a positive charge to the positive electric field. Once the distance increases almost near to infinity, that means that the energy will reduce. The energy will reduce. Where the formula will be V equal to Q over 4 pi epsilon R. Single charge. So just the difference is the R. Okay. So next. Let's look at the negative charge. Negative charge means the V will be negative. It's positive charge, all of them are positive. So this means that you look at here, still remember the formula is V equal to Q over 4 pi epsilon R. Now the difference, various R. R keep on changing. So this means negative 24, okay, is come from the formula Q over 4 pi epsilon R. Q per 4 pi epsilon R will be equal to negative 24. That means how about R if the distance increase? So this means that we need to use negative 24. Just now divide by R, right? We times with R. The R is 2. Okay. Then this means the constant. The constant is 48. 48 means that Q over 4 pi epsilon is 48. So 48 divided by 2.4. We get that it will be, this one will be negative 20. Sorry, negative 20. Okay, check, correct. How about this one? Same thing, 48 divided by 3. We get that this will be negative 16. And this one, same thing, 48, negative 48 divided by 4. Once divided by 4, we get that it will be negative 12. And next will be negative 48 divided by 8. So this means that it will be negative 6. So we check the answer. So if once all of them are correct, so we plot the graph. So this means that it's negative, right? The value will be negative. The further the distance, the magnitude of the potential, the electric potential will decrease the magnitude. Okay, negative show that there is a negative charge. Next, we look at the charge on a sphere. This sphere, if there is a sphere charge, that means that we notice that the charge are on the surface of the sphere. The distance from the center to a point P will be the distance represented by a small r, the distance. Okay. Now what happened to the P? At P, the electric field strength will be equal to Q over 4 pi epsilon r squared. That will be the electric field strength. How about the electric potential? it will be equal to Q over 4 pi epsilon r, the actual distance from the center of the sphere, okay, where r is equal to r. Yeah? What is the capital R? Capital R means that the radius of the sphere. Okay, now, next slide. Same thing, electric, what's that? The electric field for a charged sphere. So if the point is inside the sphere, if inside the sphere, what happened? Inside the sphere means that r is less than the radius of the sphere. So we use Q over 4 pi epsilon r. That means that inside there will be always constant. This means that as strong as is at the surface of the sphere, we use the r. If r, the actual distance, is less than the radius of the sphere, so we use the electric potential equal to Q over 4 pi epsilon r, the actual radius of the sphere. As a result, the combination of the two concepts, we notice that. Okay, first, for the positive sphere charge, positive charge sphere, what happened? If green, they will have the equal potential of the green color, equal potential for the red color, and the equal potential for the blue color. The combination of the charge just now for a sphere charge. A charged sphere, if the electric potential inside, what that means from this point to this point is inside the sphere, right? So what happened? Inside the sphere will constant, which the strength of the, what's that, the electric potential at the surface or inside are constant, which is maximum. And the electric potential will reduce with the distance after the sphere surface, the surface of the sphere. Okay, where inside or at the surface V equal to Q over 4 pi epsilon r, where the distance is either on the surface of the sphere or any point inside the sphere. Outside the sphere or greater the distance longer than the sphere, that means we use the formula V equal to Q over 4 pi epsilon actual distance of the point referred, the small r. Ladies and gentlemen, this is an example of the breakdown voltage of A. So if the voltage, okay, that means that the loss of the electric energy lost with great amount in shorter time. That means that it will produce spark and it will produce a very convert to heat energy, which with high temperature, where it will produce the very bright light. Another example of the charged sphere is the, what is that? This is the Van de Graaff generator. The radius of the sphere either 20 or 40. This means the difference radius. We look at here. Once what is the function of the Van de Graaff generator? Is used to collect the charge at the sphere, at the surface of the sphere. So this means if the small radius of the sphere, once the charge produced, where the potential difference is 200 watt, nothing. Look at here, 200. If the charge keep on collect until 400 watt, still nothing can be observed, right? After that, 600 starting produce the spark. 600, 800, and 1200. Observe the spark produced for 600, 800, and 1200. So you observe the length, you observe the thickness of the spark. Now, ready for 600. For 800 means that is, you notice that are not longer and stronger, brighter. How about 1200? Okay, more spark produced. How about 400? Okay, remember this one. The first produce is 600. Onward. How about 40? Once the radius of the sphere increase for 200 watt, collect again, continue collect the charge until it reach to 400 watt, nothing. Next 600, nothing happened. Next 800, whoa, also nothing can be observed. And last, this means that what is the conclusion? The greater the sphere, this means that need more potential, the electric potential to produce the spark. You see? So this means that smaller radius. This means that this shows that the electric potential is inversely proportional to the distance of R, because V equal to E over 4 pi epsilon R. Okay, according to the formula just now. As a short conclusion, the electric potential V at a point where the distance R from the point change Q, of a point charge Q is given by V equal to Q over 4 pi epsilon R, where V is inversely proportional to the R. The electric potential at a point where distance R from the sphere, from a sphere of charge Q is given by V equal to Q over 4 pi epsilon R, the actual distance, if the distance greater than the radius of the sphere. V equal to Q over 4 pi epsilon R. This means that will be the radius of the sphere if any distance R less than the radius of the sphere. Let's look at the electric field. A positive plate to negative plate. So meanwhile, in between, the line represent the electric field. What happened to a positive charge in an electric field? So as we know that positive charge and positive terminal will repel each other, where it will attracted by the negative charge plate. So what will happen? Look at here. If we choose the potential difference, the potential difference between two plates is 1000 watt. what are the potential difference? Let's see, let's observe the speed is 4.4 times 10 to the power 5. If we increase to 2000, the speed will increase to 6.2 times 10 to the power 5. If I increase the potential difference to 3000, the speed becomes faster. That is 7.6 times 10 to the power 5. And finally, if the potential is 4000 watt, that means the speed is 8.8 times 10 to the power 5. Let's look at the difference for 1000, like that, 1000 watt, the potential difference. If 4000, that means that the speed is faster. The speed, the velocity of the charge in the electric field is directly proportional to the potential difference. The stronger the potential difference, the stronger the voltage, the faster the charge move in the electric field. No matter positive or negative. Positive move from, if positive charge from positive to negative. If negative charge, that means from negative to positive. That's all. Okay, opposite direction only. Now, we observe that if what happens if there is a negative plate to positive plate. That means that the gain in the kinetic energy is equal to the loss of the potential energy. Gain in kinetic energy 1 over 2 mv squared, that's it move faster, is loss of the QV, electric potential energy. Okay, so that means that now, what is meant by QV? QV, let's say inside with a lot of charge, more than one charge, the V is the electric potential, right? Electric potential will be the energy for one coulomb of charge. If inside with more than one coulomb of charge, that means we need to times with Q. Depends on how much of the actual charge. At the end, V is the speed, yeah, equal to the square root of 2 QV over M. Ladies and gentlemen, when we use this formula, be very careful. Here, what are the two things we must be careful are the V. The small v is the speed of the charge. The capital V will be the potential difference. Okay, single V is the potential difference. QV times with Q become the potential energy, electric potential energy. So once when an electron move, that means that it will be a charge move, yeah. So that means 2 times 1.6 times 10 to the power 19 times with 2000 divided by 9.1. So we get that it will be 2.65 times 10 to the power 7 ms negative 1. That will be the speed of electron in the electric field. Now we observe that, let's say there is an oil drop. The oil drop in the tube, is it any charge? None of charge on the plate. That means that it's neutral. Due to the gravitational field, in the gravitational field, that means that this object, this oil drop, will have a weight. It's pulled by the gravitational field. So the earth pull and produce a weight. The weight of the oil drop cause it to fall down. What will happen if we put the oil drop in the electric field? Let's say if the electric field strength is equal to 2 times 10 to the power 4. Okay, so That means that 20,000 watt per meter. That is the strength. So what happened? We notice that when anything in the electric field, so they will have a wet and produce when it's in the electric field, it produces an electric force. Electric force is the F. Where the force produced, again, the force produced is smaller than the wet. So the magnitude of F is less than the magnitude of the wet. So this means that it will fall down because the wet is greater than the electric force. Once I increase to 4, this means that when the F magnitude of the F and the W are equal but opposite direction, so the oil drop consider balance. So in balance force, this means that F equal to W. What happens if the V is greater than W? Once the F greater than W, the wet means that the oil drop will move in opposite direction, where it will move to the side of greater magnitude of force. Next, just now there is a oil drop in the electric field. Now, what will happen if there is an electron? Electron move through the electric field, where the direction of the electron direction is perpendicular to the direction of the electric field. As we know that one is moving in the electric field, that means that positive will attracted by the positive plate and repelled by the negative plate. Look at here. Okay, for certain speed. Next, I will increase the speed of the electron. Once the speed of the electron increase, we notice that the angle of deflection reduced. I increase again. This means that you notice that when the speed of the electron increase, means the angle of deflection reduce. Okay. Next, what will happen if I increase the electric field? Just now, like that, same speed, yeah, the electron with the same speed, but with stronger electric field. Okay, stronger electric field, that means it's deflect greater. Another one means that what happened? What conclusion we can make? That means that the deflection of electron by the electric field increase when the electric field strength increase. The angle of deflection is directly proportional to the electric field strength, but inversely proportional to the speed of the electron. Again, the angle of deflection is directly proportional to the electric field strength, and the deflection of the electron by the the deflection of the electron is inversely proportional to the speed of the electron in the electric field. Next, look at here. This is a positive charge. Positive charge in the electric field, they are in parallel. That means that the positive charge will follow the direction of the electric field line. But electron will always flow in opposite direction. Positive will follow, right? When it's the direction of the voltage, the direction of the positive charge in the electric field. but the direction of the motion of the charge is perpendicular to the electric field. What happened? It will form a curved path. And if electron will in opposite direction. Okay, that is the path of the motion of the positive charge and negative charge in electric field. Consider the electric field with the same strength. Ladies and gentlemen, as a conclusion, we can say that when a particle of charge Q is accelerated through a voltage V, gain in kinetic energy will equal to the loss in the electric potential energy, where 1/2 mv squared is equal to QV. Ladies and gentlemen, be very careful. The small v is the speed or velocity of the electron or of the charge, and V will be the potential, the electric potential. If there is an electron, M will be the mass of the electron. If there is a proton, this means there will be the mass of the proton. Next, velocity of particle. V equal to square root of 2qV over the M. Okay, where M is the mass of the particle, Q how many coulomb of the charge, and V will be the potential difference, the capital V and small v. So ladies and gentlemen, once you answer the question, when you write the equation, because you are used handwriting, right? So be careful, yeah. The 2V. Make sure you write one small, one bigger. Okay. Next, a charged oil drop stays stationary in a vertical electric field when the electric force acting on it equal to the weight of the oil drops. An electron entering a uniform electric field at right angle travels in the parabolic path. And last, the deflection of the electron depends on the velocity of the electron and the electric field strength. That's all for today's lesson. And then, student, later I will send the question, the worksheet, to our Telegram group. So these are the questions. In the worksheet, we have question 1, question 2, question 3, question 4, question 4, question 5, question 6, and question 7. Last, question 8. So, I hope that student, okay, instruction for all students, make sure you try this question and solve all the question. Thank you very much. So I left you all to solve the question for the rest of the time left. So, ladies and gentlemen, I stop the lesson for today, and we continue again tomorrow. Thank you very much, and have a nice day. See you. Bye-bye.